That means I gotta go say it's recording over here. Okay, I can put this up on the screen. I just have to figure out where it is. Just a second. Now, also, I want to talk about a little bit about WebAssign today as well. But let me go to this, see if I can get this to come out. There it is. Yeah, okay. Now, you guys at home ought to soon be able to see what I'm going to show the people here have in their possession. Just a second. Okay, hopefully. Right. Okay, so everybody should have a page on the screen now that says Proposition 0.1. There's like people in present here have a piece of paper that says that. And we want to talk about why we have these two theorems, two propositions. What I do here on these pages, I say a proposition is like an assertion. It's like what we believe in, but we haven't proved. Then I actually prove it, and then it becomes a theorem. Theorems are things you have proved, okay? And so I start out by saying this is what I think is true, then I verify it, and I call it a theorem, all right? So equivalent limits, and again, I'm going to write big on the screen, on the blackboard. I don't know how easy it is to see at home. You guys can all tell me, those of you here today, if you're not here tomorrow, again, we can communicate, tell me how bad it is, and whatever. I hope everybody can live with what we got for a while. That's one reason I'm giving you paper, so that you have something to look at instead of the board. Anyway, we are talking about limits, and limits are heading someplace. I'm going to set all this up here in a second. And the one thing we're talking about, sorry, is, I have to make sure it's A. One thing we're talking about is a limit, and the other thing we're talking about is a second limit. And we're still heading to the same place. What you will see on your screen or in the paper here is that I have some assumptions at the beginning. One is a letter D sub F. That's just a set. And it says I have a set of real numbers. I have a function which is real value defined on that set. That's just what you're used to seeing, a graph and things on the X, Y axis, okay? I'm taking a number A in the real numbers, and the X naught is a member of DF prime. Remember what that means? That means X naught is an accumulation point of the domain. That means I can get close to it. By X is in the domain, I can get close. That's what it means, okay? So basically that's the setup. Now, so the X naught is things I can get close to, same X naught in both cases. This says the function values are heading toward the number A when X is real close to X naught. This one says the difference of the function value and A get close to 0 when X gets close to X naught. And I hope that that's like obvious. If I get close to him, which I'm not supposed to do right now, but if I do, approaching him, the distance between us goes to 0, okay? And we take distance by subtracting. And so all basically it's saying is when f of X approaches A, the difference approaches 0. If the difference approaches 0, they're approaching.
Okay, so
Okay.
closer.
I'm sorry.
Did they just end up getting closer?
Yeah.
Okay.
Well, the X is approaching A. Basically, on a picture, you know, you have an X naught here, and somewhere you have an A. It wouldn't necessarily have to be positive. But what we're saying is, when you get close here, you get close up here.
Okay.
Or when you get close here, the difference here gets small.
Okay.
Now, the nice thing about the proof, and you guys got to get used to epsilon delta proof, all right? It's what it is. when you write down what you mean by the epsilon delta proof of the first one, and you write down what you mean by the epsilon delta proof of the second one, just write them out. Okay, that's what I did in the proof. It says limit f x if and only if. Now, after the if and only if, you can see the epsilon delta thing. So look at the whole sentence that starts with IFF. And then look at the next line, the whole sentence that starts at IFF. One of those is the first definition, and the other one is the second definition. That's writing out the epsilon delta thing for the top thing on the board here. The other one's writing it for the second thing on the board. Now, how are those two statements, those two sentences different?
They're different at the end. One has a minus 0 and the other one has.
In one, you subtract 0, and the other you don't. What's the difference when you subtract 0? There isn't any.
Yeah. So
Therefore, if you believe one, you believe the other, and conversely. So once you write down what you mean, it's the same thing. So sometimes we're going to prove that f of x goes to a. Other times we're going to prove the difference goes to 0. The point is we now have a choice. It's always nice to have options. I go to my house on this street or I go on that street. It's nice if I can go different ways. So if something's blocked, there's a fire or some fire engine or something, I can go another way. Okay? It's always nice to have options. Now, so that's little proof. I mean, if I ask you guys to prove it, like, oh, it's horrible. Once you write it down, it's like, I don't have anything to do. You're right, because it's so easy. Okay, but you got to write it out properly, or you won't see how easy it is. Okay, the second one is harder because you have to worry about something a little bit. So the second one is got more junk attached to it, so it seems like it's more difficult. But what we're trying to say is not more difficult. It just will seem like it. So what I'm going to talk about, again, is two limits. One, I shouldn't have erased. One of them is just the same thing we had before. Okay? And the other one is, well, I'm going to have to change that in a second. The other one is f of x naught plus h equals a. So these differ from the previous one because before I had 0 on the right-hand side, but this now changes. So let's talk about what these are. Two different things. Second proposition. And so right now for you guys at home, probably it's easy to see, well, I don't know if it's easy to see on the screen, but what I wrote on the screen is less messed up writing or less complicated writing than what I just wrote on the board. I wrote the two things I want to talk about here, not all the stuff we need to do it. So basically, let's see what this would mean on again, a graph. I want to approach x sub 0, okay? And so I want to approach x sub 0 because that's what the limit is. Now, if I call the difference between x and x naught h, okay? Now, the x is going to be varying, and so the h is going to be varying. I'm going to pick different x's so I get different h's. Now, what's going on here? The difference between the two things is the h. Again, we're talking about distance between. What did we do a minute ago? We said when I get closer, the distances go to 0. Well, now I'm naming the distance. But I'm saying if f of x is close to a, what does, now, the variable here is the h. So the x naught is fixed here, okay? If you look at x minus x naught, if I write what x is, it's x naught plus h. So basically, roughly, if I were to get rid of x and write x naught plus h there, that shouldn't change anything. If the h is going to 0. So I think intuitively it makes sense. Now, the proof takes half a page because to set it up correctly, remember we only take limits at accumulation points. So how do I know that 0 is an accumulation point of this function?
You would plug 0 into the formula.
Well, the problem is
You know,
I got domain problems. The function's only defined in certain places. So this is only going to be defined in certain places. Because if my domain is like this and my x is picked out here, then the h is going to be too big and stuff, you see? I have to be careful with the domain of the function and getting close. So basically what I've got, and again, I don't know how this is going to show on at home. I seem to want to say A here. Where I have a 0 someplace. And so what I'm doing is taking an x here, and that distance would be this distance right here, around 0. So all I'm doing basically is shifting the graph, sort of, from one place to another in terms of what I'm doing, this is a composite function. And since it's a composite function, it's complicated. So what's the proof do? Not writing, you need to stare at the thing and study it, but the proof of 1 says, what's 1 say? 1 says x is an accumulation point of the domain of f, if and only if 0 is an accumulation point of the set H. And the set of H is the stuff around the origin. And conversely. So if I take something close to the origin, that's, if I think of going off of x naught by that same distance, that's close to x naught. And if I go a little bit off of x naught, that's going to be a little bit off of the origin of that distance. Anyway, so number 1 is trying to show that I can take a limit because you can only take limits at accumulation points. So this is accumulation point. How do I know this is? I have to prove it. Or this is accumulation point. How do I know this one is? I have to prove it. That's what number 1 is. Not very long, a couple, 3 sentences. And then the second half is that the limit, I see I wrote a 0, it's a letter O, and no, it's an A, okay. So the second half actually writes down the epsilons and delta argument, which shows you it's true. Now, I want to show you why we want to have such things, okay? The second one here, I want to do a little proof of something that we haven't talked about before. This is not in the notes, so those of you at home, I hope you can see this. I'm going to start over here, and I can't see myself now. But how do we prove what happens to the sine function as x approaches 0? And you're going to see in a minute how I shift some things, but it'll take a little bit of work before you see why I gave you this handout today. Okay? How do I prove what this is? Now, what do you think? Do you think this sine is a continuous function?
it looks like it will.
Graph and all that. You've had that from high school. Okay. So what do you think the answer is to this limit question? As x goes to 0, what does sine of x do? Goes to 0. The sine of 0 is 0. So what I'd like to prove is that that's true. Okay. Now, so I'm going to try to prove it. I will also probably be writing this down later so you can have a handout and all that kind of stuff, because I don't know how well this is showing up at home. So anyway, so how do you make a proof of a limit? You have to take an epsilon every time. Okay, take an epsilon greater than 0, and I'm going to have to choose a delta. Remember, the next thing to do, if we knew what the delta was, is to choose one, and then we're going to take something in the domain of the function. The domain of the function for the sine function is any real number, and we're going to assume always the if part of the if-then sentence, which is, in this case, 0 is less than delta, and we have to say, so what I'm doing is writing out the like prototype. This is what I'm trying to prove. So this would become a proof if I knew what the delta was. But I might have some extra lines in here in between things to verify the statements I'm making. But you always, and again, you guys can sound off at home. Can you see what I'm writing on the board? I have Sean says he can see.
I'm having a hard time.
Anna, can you see okay?
Is there any way you could take like the notes off of our screen?
Talking, but I'm not hearing her.
Professor Akipio, she says that she would like for you to stop sharing your screen for the notes. You know how you're sharing the notes with the people who are
Yes.
online? She says it would be easier to stop sharing.
Not just easier. Thank you. Please sound off. I think you can see the screen. I didn't turn off the share. Okay? You guys, this develops your psychic abilities because you had to see the screen that you couldn't see. And so,
Or you didn't see it.
you understand, I still had on that first page on the screen. They couldn't see a thing here. They tried hard.
So you might be able to see.
Okay, so so we want to talk about the limit of the sine function as you go to 0. Okay? And I take an epsilon, I'm going to choose a delta. This is just the format you always use. I will take something in a domain, assume it's a certain size here, and try to show something. That's what I'm going to do. Now, what you always do is go over to the side someplace because I need to figure out how to do the delta. And to do that, I look at the then part. I'm supposed to show that the sine of x is less than epsilon. That's what I'm supposed to do. Okay? I don't know how to do that yet, but that's what I'm supposed to. Now, what am I going to know? I'm going to know that this is true. So let me rewrite this a little bit. What I'm going to know, just without the 0, I'm going to know that absolute x is less than delta. I'm going to know that. When I get to this part of the proof, to do this part, I will know this already because it's already before. Okay? So when I get around to doing it, I'll choose this, I'll do all that. This, I'll know all this stuff. Then I try to do this. That's the game. All right. Well, what can I do with the sine of x? I'm going to know x is less than delta. You may remember that a few days ago, we said that the sine of x is less than or equal to x in absolute value. If that's true, and absolute x is assumed to be less than delta, then I've got the thing I want to be less than epsilon, I've got it less than delta. But I get to choose delta. I want to end up with epsilon, I've got delta, and I get to choose delta. Answer, choose delta to be epsilon. Then, as far as this proof goes, I'm just going to rewrite it slightly. Okay. So now I'm going to write out the proof. This is less than or equal to this. That's less than delta, and that's equal to epsilon. That's the proof. So we now know that the sine function is continuous at 0. Okay? That's the proof anyway. So you guys might not know, but I know the sine function is continuous at 0 because I just proved it. If you don't believe in this, you do. I don't care if you believe it or not, but we just did it. So I will assume from now on we know that. Okay? Now, how about the limit of the sine function at, as I approach, I don't know, pi over 4? About that. You think the function is still continuous. So what would the limit be? Continuous function, you get to stick in where you're going. I'm heading to pi over 4, so I get to stick in. So I gotta know the sign of pi over 4. Review trig for a week, okay? Square root of 2 over 2. That's what I think the answer is. I notice it's getting worse. 0 is nicer. Okay? So how would I prove this? Now, I'm going to tell you ahead of time, if you're copying, it's not going to work. All right? So whatever you do here, you later say, you have another proof. Because the first thing I'm going to do here, I mean, I just did this, and if I'm you guys, I kind of understood it. Maybe for the first time, I was like, whoa, I'm beginning to get this. And now I'm going to do this over here. And if you were home doing it, you would get very depressed because it's not going to work. But I don't know that yet. Okay? So, let epsilon greater than 0, choose a delta, and so on. Same process, okay? Except, what's the, where am I? I'm over at the end here. What's the then part now? I have to do the sine of x minus the square root of 2 over 2. I have to make that less than epsilon now. And what am I going to be given? What's the assumption going to be? The assumption, I'm going to be given that 0 is less than x minus pi over 4 is less than delta. That's what I'm going to be given. Now, what do we do over here? Over in this thing, I had to do something with the sign, and I had something to do with x, but I had a relationship between the sign and the x, so I could use that relationship to make it easy. Now, you guys tell me, how do I find a delta if I let x be close to pi over 4? How do I find a delta so that the sine of x is close to square root of 2 over 2? There's no, see, once I get to the sine function, if I had algebra here, I can factor and stuff. But I don't know what to do with this one. Yes?
McKinley is in your waiting room.
I'm sorry?
There's someone in your waiting room.
Ah, I'm in the waiting room. How much do they want to pay? Mackenzie, thank you. If it's, no, Miss McKinley, I think, right?
Yes.
Yeah, sorry you weren't, I can't, yeah, anyway. Everybody that came today is now clairvoyant, but I'm not clairvoyant, so I didn't see you. Anyway, okay, the point is that this idea, which I just tried to make work, there must be a relationship between these two, but I don't know how to find it, you see? So maybe it makes sense to do the page I gave out earlier that everybody except McKinley saw already. And so let's try, instead of doing this, so let's try to switch over to the second proposition that I showed you. Let's try to show that the sine of pi over 4 plus h, as h goes to 0, is the square root of 2 over 2. This is the alternate thing that I proved earlier today. In the guise now of the function f is now the sine function, and the x naught is now pi over 4, and so forth. Okay, does everybody understand? I changed the x to x naught plus h. The x naught is pi over 4. There's the pi over 4. This is a translation into specifics that we did earlier in more general. Okay. Now, what do? So I'm going to outline it. This is what I'm going to prove. And what's the proof going to look like again? The proof, you're going to take an epsilon, because we always do that. And you're going to choose a delta and so on. All, hopeful. We're going to do the same thing I did earlier. But what do we do to choose the delta? We look at the then part. Remember, in the if-then sentence. What's the then part? Now, I think what I'm going to do is go in the middle board here. This isn't very good in terms of you guys taking notes in class here, but for people at home, I think they can see this better. Okay, so the then part will be that the sine of pi over 4 plus h minus square root of 2 over 2 is less than epsilon. That's what I still have to do. Now that maybe doesn't look very different than what it did a minute ago. A minute ago it was sine x minus square root of 2 over 2 was less than epsilon, remember? Now, but this is different because I see something to do with this one. Namely, because I reviewed trig, that's the sine of pi over 4 cosine h plus the cosine of pi over 4 sine h minus the square root of 2 over 2. That's what that equals. I'm trying to prove it's less than epsilon, but that's what it equals. What's the sine of pi over 4? Square root of 2 over 2. What's the cosine of pi over 4? Square root of 2 over 2. So rewriting this, I have square root of 2 over 2 3 times. I can take it out. So I have a square root of 2 over 2 times the cosine of h plus the sine of h minus 1. See? Now, okay, what I'm trying to show you first here is, and I may not be able to finish it today, I may have to know something else, but the idea that I wanted to show you is by changing the thing and shifting it, I was able to do something. I changed it completely to trying to make these things small. Now, what happens to the sine of h as h goes to 0? Because we just proved that this is true, right? So this is going to go to 0. What happens to the cosine h minus 1? Yeah, but we haven't proved it. So the game I'm trying to get into your guys' head is discovery. I proved the sine of 0 goes, sine of limit goes to 0, at 0. Now I want to do it at pi over 4. Oh, that's a natural kind of thing to progress to, okay? To do it someplace else. So I'm right now, but I couldn't do it directly, so I changed to this. This is because I was able to use a trig formula that you're supposed to know. Okay, so it gave me some distance to go here. I made some progress. And now I find out there is something called the triangle inequality. The triangle inequality says if I have a plus b in absolute value, that's less than or equal to absolute a plus absolute b. You guys are supposed to know that. We've already used it in those other notes I gave you. So I can replace this cosine h plus sine h minus 1 with absolute cosine h minus 1 plus absolute sine h. Now, we know that the sine h goes to 0, right? The point is I got two functions here now. So if I could prove that the cosine goes to 1, then I've got this goes to 0 and this goes to 0. And so that gets me to, I still haven't found the delta. I told you, this is like discovery. You go along and you say, oh, I can't do this, so I do this. I go along a little further and I say, well, if I could just get that this cosine h goes to 0, goes to 1 when h goes to 0, then I got this goes to 0, that goes to 0. That's going to enable me to find the delta. So I've got to do something first, though. In order to do this, I need to show that as x goes to 0, cosine x minus 1 is 0. So what's that? That's another epsilon delta proof. So when we're just beginning, we have to prove things about algebra. We have to prove things about roots and squares and things. And we have 6 trig functions. We don't know that they are continuous and limits and all that yet, because if you hadn't had calculus, We haven't done that before. So we got to verify it. And when you have to verify the stuff at the beginning, you have to do epsilons and delta. That's all we've got to prove it. Okay? So I now have to worry about proving this. Now, I'm not going to do that today. I wanted to show you how we do stuff so that all those notes I gave you the other day, all that written out stuff, I didn't sit down and start writing that like a letter. You know, some of that takes hours to do. But what you do is you figure out what you got to do, and then you sometimes say, oh, I got to do this first, I got to do that first. And so you don't show people, it's not like writing a novel. You decide at the end they're going to catch the murderer or something, but you have to put in all kinds of things in between. You know, there's certain, it looks good for people, it looks bad, somebody's accused of something, making a novel. They put in stuff. And I don't know how much the author has in mind when they begin of how complicated the plot's going to be yet. I think they do stuff and they, oh, I can't do that without killing off somebody else. And, you know, I think it gets more complicated and then they decide this is enough. It's 400 pages and I'll make $1 million and that's enough. So anyway, well, with this game, you start out, you try to do something. Sometimes you're successful and sometimes, well, I have no clue. Other times like, well, why don't I try another option over here? So what I'm going to do is write all this out for you as if I saw exactly what to do all at the right time. You see? So I wanted to show you first day in class, I wanted to show you a failure, so to speak, or at least not a smooth thing, because that's the way math is. You have to struggle with it and see how it works and play with it. If you don't, you will not learn it. That's just the nature of the beast. Okay, so what I want to do now is do some other stuff and take care of this later. But it's partly related. In the notes that I gave you the other day, you're supposed to get down that this is 1. And it's in your notes that you've got. We talked about it already. You trap it, you use the squeeze theorem to do it. Let's assume for the moment that we believe in it. Okay? Let's assume we believe this is true. Now, warning or danger or whatever you want to say, this is only when it goes to 0. Now, some people learn this and then later I get on a test or something, I put x goes to 5 and, you know, and people say, oh, it's sine x over x, 1. Because you get programmed for the one you don't like, do you know what it is? And you think I'm going to ask you that one. So you put down 1. What should you have put down for this limit? Well, sine we're going to prove is continuous. Haven't done that, that's what I just erased. Okay. Sine is going to go to sine 5, x is going to go to 5. That's the answer. Once we know the sine function is continuous, you get to stick in where you're going. Unless it's 0, then you can't. So this you have to do independently, but any other number you just put in where you're going. Almost. Because if I change this to this, now what? What happens when you go to infinity? Because one of the things we got to practice and learn about is infinite limits. We got to go to infinity and we got to talk about function values going to infinity. Now, how big can the sine ever be?
1.
Biggest it can be is 1. How big can x be if x goes to infinity? Infinity. So now, if you play games with symbols and you say, well, I'm just going to write this. This is wrong. If you write this, I will put red all over your papers. It's wrong, bad, and all that. Now, why is this bad? Because I have no clue as to what the sign of infinity is. Okay? Now, you don't want to, you will do this anyway, but you're not supposed to. What you should be doing is saying, how big can it get? how big can the numerator get compared to how big can the denominator get? And what you do here is you say, hey, this, is less than or equal to this. Because the numerator is never bigger than 1. What happens to 1 over x as x gets really big? It goes to 0. We haven't stressed it yet. It's in some notes, it's coming. But the graph is going to look like this when we get around to graphing. As you get further and further out this way, it goes to 0. So if I had to prove something here, this is going to be related to this, and now this is going to go small. This is going to be less than whatever. And so this is going to be small because this is going to be small. So if we prove everything, okay, the idea is if the numerator is bounded and the denominator is not bounded, the answer is 0. And we could prove that. If I put cosine here instead, same thing. But you put cosine here, not the same thing. Okay? That's different, completely different. Why? Because the cosine of 0 is 1.
So that would be undefined.
So this is 1 over something going to 0.
So it doesn't exist.
It's not defined there, but it's also going to be infinite.
When it not exists,
So anyway, but you have to be careful. You can't just say, oh, I know one thing, so I can just generalize. Okay? Can't do it so fast. Okay, so anyway, just wanted to point out, we can talk about limits elsewhere. I'm trying to prevent people from making mistakes later. When we change this number on you, always look and see where you're going. It's true in life too. You get near stairways, look down. Okay? You need to know where you are and where you're going. Okay? Sometimes it's important to know where you've been, but it's often very more important usually to know where you're going. Okay, now I want to do something else here. What if I have, I don't know, I'm just making up something here. Now, again, I told you I'm going to be giving you notes. Part of the notes are going to be talking about what happens to the cosine. I haven't given you those notes yet, but we've already talked about, so I'm kind of trying to use what we talked about earlier, even though I know I haven't given you a nice worked out deal yet. What's going to be interesting is when you guys want me to prove it to you, rather than being afraid of a proof or not liking them. If I fail to do something, one of these days, say, hey, you didn't do so-and-so, and then you crossed over to wanting to see why. That's part of being in the class, okay? Okay, so how we do this problem? I'm sorry, I can't.
You were supposed to plug the 0 into the x's, but then you learned that that doesn't really work because that would be 1 over 0 over 0. So you would do the.
Are you saying this? That's not what you're saying.
No.
That's good because that's wrong. By the way, I think you can lower, I have trouble understanding. I said, no, don't take it off. I think you can, when you talk to me, I think you guys can lower your mask. That's up to you. But I believe we're far enough away that you can talk to me, like eating. I'm the one in danger around here, you guys know, not you guys. But I'm the one risking my life to be here. Anyway, I don't know what you said. I'm sorry.
Okay. So I'm saying you substitute x for 0 or 0 for x in the.
If I do this,
you get 0 0. So then you would do the.
there is no such thing as 0 or 0.
So then you would do the thing we did yesterday where we did.
Well, yeah, okay. So you do that wrong.
Okay.
Okay, you get something wrong. This is when there might be an answer. If I do this kind of game and get this, that's no problem, that's 0. If I do the kind of game and I get this, it's going to probably be plus or minus infinity. Okay, maybe it's one-sided then. Maybe you have to approach from the left or right before you can make a conclusion. Because maybe this means the graph looks like this. Anyway, we're going to get into that. But if you have this is like, this could be 1, it could be 55, it could be non-existent. This is we don't know yet. So you do that just to help you a little bit. I wouldn't do this because we don't know anything about 1 over x. However, what you do here is multiply numerator and denominator by a conjugate. Sometimes it's a good idea, sometimes not. Okay? If I do that, the numerator becomes 1 minus cosine squared. The denominator is more complicated, but not bad. What's 1 minus cosine squared? Called Pythagorean theorem. Sine squared. So I can rewrite the numerator, and I hope everybody at home can hear me all this. You write the numerator as sine square over 1 plus cosine x times x, as x goes to 0. Now, I think you can see better if I'm in the middle. Anyway, what do we do with this thing now? Well, this up here, sine x over x, is going to help us. Because what I got over there is I got sine square x over x. Well, I'm going to always look around what you have before you take limits. There's no reason to even have a limit here yet, except we carry it on. If I write this as sine x over x times sine x times 1 over 1 plus cosine x, in other words, I split these things up as all products, I can split them out. And look at the 3 things I got. What happens to sine x over x as x goes to 0? Goes to 1. What happens to sine x as x goes to 0? Goes to 0. What happens to cosine x as x goes to 0? 1. So this is a half, this is 0, and this is 1. What's 1 times 0 times a half? Got my answer. Okay? Now, so multiplying by conjugate here. So this is a second thing that you will need to put to your memory when you have this kind of a limit. What was the answer? 1 or 0? You might forget. I think it's 0. If you don't, you have to go through the proof again. Okay? So now, let me just real quick, let's try something else just for kicks. What happens if I try the same trick with this, 1 plus cosine? If I do this, get this. Oh, sorry. Get this. Okay. Now, do you think that's a good idea? Now, let me try to explain. What I did here is I tried to get rid of the x. I couldn't get rid of it, but I replaced it with something that balanced it. If I can't get rid of it, I nullified it. Okay? Because of this. But up here, if I do this, what am I doing to the denominator? See, x is going to 0, so there's a 0 there. If I do what, stick in this place you're going. You get a 0 down there, that's bad. What happens to cosine x as x goes to 0? So what's this? This is going to be 0. So what did I just do? By this process, I introduced another 0 in the denominator. That's probably not a good idea. So the other day we talked about this. This is 23 after. The other day we talked about this multiplying by conjugates. Sometimes it's a good idea. Sometimes it's not a good idea. That's why you have to do problems. You have to see what is